All right, let's get started with my ECE404 LNA design. I'll be going through my design process. Let's start with the project description. So this is the design parameters that we had to follow for the project. The device had to have a center frequency of 915 megahertz, S11 and S22 values under minus 8 dB. And then we had a gain, which is S21, which had to be around 12.5 plus or minus 2.5 dB. We need to have a noise figure less than 1.5 at 915 megahertz, a substrate area of 2.5 inches by 2.5 inches, and then the device had to be stable from zero point 0.1 gigahertz to 5 gigahertz. So these are some of the initial calculations that I based my design off of. We have the equations on the left side of the screen, which is represented with that table. These design calculations can be done via ADS. And so that's what I based a lot of my design off of because ADS allowed me to simulate a bunch of different gain and noise figure situations a lot faster than maybe doing these by hand or by writing a MATLAB code for. So on the right, we have the different icons for all the calculations that I used or all the circles that I made using ADS. So we have our GS circle, which represents our gain circle. This will be shown on the next slide. I have gain circle. This will be the source side of my gain. Then I have GL circle, which is the load side of my gain of the transistor. Then I have L stability circle, which is the stability circle. So outside of that area for my design is the stable region. And then I have source stability circle. So again, outside of that area is going to be my space that I want to design around. It's going to be stable. And then on the bottom here, I have my noise figure circle. So this is how I got my noise figure. So in this example, I have a noise figure of 1.4. And on the next slide, I'll be showing you how I went through those simulation process and how I use these different calculations to solve for my final LNA design. So here are my initial simulation results. So what I did is I first needed to understand the maximum gain that can be done based on the biasing. So first I went through and tried to find biasing that worked best for our 12.5 dB gain. And I found that 1 milliamps for the biasing of the transistor was the best because once your biasing is set, your G naught cannot change. So the biasing with 1 milliamp had a G naught of around 10.35 dB, which was very close to our 12.5 that we had to work around. So I didn't want to go any higher than that because it would have been working with different G naughts, which can only be set with biasing. So once I had my G naught set and I knew my biasing, I then went to my Smith chart shown on the bottom of the screen, and I wanted to match my source and my load. So initially, I have a noise figure of 1.4, which is represented with the red circle on this graph. I then have a gain circle, which is the light blue circle. And my gain that I was looking for was 0.5 dB because I wanted my load circle to be 3. So if we added all of those together, we get around 13 and a half dB, which would be a good gain for my S21. So I then have my gain load circle, which is the gain load circle, which is this brown circle here, which represents 3 dB, as I mentioned earlier. And then I have my two stability circles. So I have my source stability circle is the pink, and then my load stability circle is my dark blue. I then have two squares on the screen, and those show intersection points between this initial one here, this light blue one, is where the noise figure circle intersects with the gain circle. And what this tells me is that if I design my system or my source side around this square where these two interact, that I can get a noise figure around 0.4. I then also have this other red square, which is where my load circle interacted with my noise figure circle, guaranteeing that for my load side that I could also be getting about 0.5 noise figure. Once I had these initial points on the Smith chart, I then had to match those. So on the next slide, I'll be matching those. So on the left, I have my source side matching. So they interacted around this point here, which is where I put my load. And then I matched that based on that interaction while also considering the different biasing and protection that we needed for our circuit. So I have this capacitor here, which should be our DC block. And then also this inductor here, which will be part of our biasing circuit, but I also try to use it as our matching as well, something that was discussed in class. Then I have my load side. Again, we have an interaction near here, what we saw in the last slide. And I again use this inductor, which will be used for our biasing circuit, and then matched off that as well. So that was useful. It made my biasing part a lot easier. And once I was able to start with these values, I was able to add a couple more of the design parameters that we needed or the safety considerations that we needed. But it made that process a lot easier, and it made it so that when I was getting to those points, that it wasn't changing my response or my system too much. So these are the two matching that I did. And I'll be moving to the next slide where I kind of combine these two matching, tune, and then add biasing. So we'll see that final design. So this is my final design here. As you can see, this is the source side here. We have our DC block that we considered in that initial design. We also have the line here that represents a smaller width than what we normally use for our different connections. And then also our inductor here. So this is the source side here, kind of cutting off at the inductor. After that, we have our RF short or RF isolation. This is something that we talked about when protecting these biasing resistors in class. This is a concept that helps it so you can still use this inductor for matching, but then also be able to properly bias the system. So then I have my two resistor values, or three resistor values here actually, that I used for biasing. So you have my 5 volts on the bottom here, and I bias based on what my initial biasing was in my simulation. Now those values were eventually tuned, and I found the right biasing that worked for the way my matching was set up and the way that the rest of the system was set up when there were more considerations, elements, losses, things like that. And then as we move to the load side here, same kind of thing. We have our inductor that we saw at the start, and then we have this stub at the end, and then our DC block as well, with an RF short on the biasing side of the load. So I was able to integrate what you saw on the last Smith chart into this full system. It did take some tuning and some time to get it all to work properly. There were some parts that maybe weren't added or that couldn't be done with the Smith chart, like this RF short device. It was hard to make that with the Smith chart matching, so it was something that had to be done after the fact. But I believe that this design with the matching that was done before, along with all the DC biasing that was done and the protection for the DC biasing that was done, was able to meet a lot of the simulation results that are shown on the next slide. So I'll move to the next slide. So this is the final design. I'm happy with the results we saw from it that we'll see on the next slide. So these are the simulation results. So I was able to hit the noise figure of about 0.396, which is under the 1.5, S11 and S22 below the -8 dB. As you can see, I was able to hit an S22 of -9.6, and then an S11 of -15.5. I then also had my S21 in between 10 dB and 15 dB with it around 13.351, which was actually quite close to my initial design when it comes back to the start, where I was looking for around 13.5, 14 dB there. Then when I look at the stability chart, my lowest K value is 1.1, and that's around 5 gigahertz when that happens. And then my maximum mag delta value is around 0.519, which again meets all the stability that is necessary for our circuit. I was happy with these results. I think I was able to hit everything I was looking for. One area that I would maybe improve for the future is looking at making this noise figure around 5 gigahertz a lot more stable. Though I was able to reach the intended noise figure value at the frequency that was necessary, it would be nice to have less noise in the entire system, just to make the system a little bit more stable. Moving to the measured results, so I was able to get my board manufactured and pick it up. So when I measured after using the Nano VNA device, I tuned or calibrated that Nano VNA device, and then I was able to get measurement results. So for S11, I was able to get -14.297, which comparison to the S11 value I had here, it was very close to the initial S11 value I had in the simulated results. fitting the requirements that we had. And then an S21 value, I was reading at about 6.691 dB, which was about half of what I was seeing in my simulation results. And so I wasn't able to meet the exact requirement there, but still able to get a decent gain at S21. So these are the two graphs that I got from those simulations. So this is S11. This is the return loss I saw there. And then this is S21. Obviously, we can see I have multiple markers here, but the most important being at 915, where I was getting 6.91 dB. So I also have my final layout here. It took a lot of time to get this layout exactly how I wanted it. A lot of moving elements around, making sure that the transistor tolerances were at the right point and that they fit what we were looking for so that the design could be properly assembled. Moving to the conclusion, I found that the simulation results were all met. So my S11, S22, S21, along with my stability and noise figure, were still able to reach what I was looking for, but my measured results were off by a little bit. It was nice to still get my board manufactured and being able to measure it as well. It was great to see the simulated versus measured. So I was able to meet most of the requirements, stable for most of the frequency range, which I was happy about. I did see some noise or instability at the end here. So from about 0.1 to about 0.45 gigahertz, I was able to get a reasonably stable and noiseless system. And then my S21 just missing the design requirements, but still happy with the results that were received. So that wraps up my presentation. If you have any questions, please let me know, and thank you.